Welcome to today's lesson. We are going to look at applications of uniform circular motion. And the first one that we have is a car rounding a level circular bed. When a car is going around a circular path on a horizontal road, the centripetal force required to maintain that body or that car in a circular path is provided by the friction force. And this is the friction force between the tires and the road. Therefore, we can say that mathematically we have Fc is equals to Fr. But we know that our Fc is equals to mv squared over r. So this value or this expression will also be used to calculate our friction force. But sometimes you find that when the road is slippery, that friction force may not be sufficient to provide the centripetal force. And as a result, skidding may occur. Now, to provide skidding, we ensure that the cars do not exceed a certain speed limit, and this speed limit is referred to as critical speed. This speed depends on two factors. One, we have the radius of the bed. One may negotiate a bed at a higher critical speed when the radius of the bed is bigger. Then the other factor is condition of the tire and the nature of the road. When you have new car tires and a rough road, these two combined will give us sufficient friction that is necessary for the centripetal force, and therefore you find that skidding is not likely to occur. Then the other application is when we have banked tracks. Now this is when the road is raised gradually from the inner side of the bed. In this case, the banking angle is in such a way that the centripetal force is no longer given by the friction force, but the centripetal force is given by the normal reaction of the road. We can consider a car of mass m and traveling around a bed of radius r with a speed v. When you have that case, the bed is banked at an angle theta, and therefore if you look at the diagram that we have, this is the banked road, and now this is our diagram that is representing this. So we have our car here. The banking angle is theta, so we have that the force that is acting towards the center is r sine theta, and the normal reaction or the force that is acting upward is r cos theta. Remember, we are considering this angle, and this is our weight, that is the weight of the car. Therefore, we have that r sine theta, this force will give us the centripetal force, while r cos theta, the magnitude of this, if you look at r cos theta and the weight, they are in the same line, so they are action and reaction. Therefore, they are equal in magnitude but different direction. Therefore, the magnitude of r cos theta is equals to mg. If you look at the first one or the second one, you can get that cos theta will be given by mg over r. Then in this first one, we have r sine theta is equals to fc. So our sine theta is equals to mv squared over r and capital R. We have differentiated these two r. This is the radius of the circular path, and this is the normal reaction. If you look at this part, mv squared over r is giving us the centripetal force. But we know that tan theta is given by sine theta over cos theta. So if we divide these two terms, this is the sine theta, which is mv squared over r capital R divided by mg over capital R, you will find that we are dividing, so we multiply by the reciprocal, and you'll find that the capital R and R, that is reactions, will cancel out, and mass will cancel out. So you are left with v squared, which is here, and then we have rg. V squared over rg is equals to tan theta. So you can be able to get the value of v, and v will be the square root of rg tan theta. If you look at this expression, you will find that this critical speed actually depends on two factors, radius and the theta. If you look at g is a constant. and therefore critical speed depends on the radius and the banking angle. Then we continue with a cyclist moving around a circular track. In this case, the friction force is the one that is providing the centripetal force. Remember, we need this force so that an object or a body can move in a circular path. So if frictional force is not sufficient, again, you will find that skidding may take place. And now, to avoid skidding, when the cyclist is moving around bed, you find that they lean inwards. We can have like the second case here. The first one is moving very straight without leaning, and therefore the friction force is providing the centripetal force. But if you look at the second diagram, he is leaning, the cyclist is leaning, so that now these two forces, reaction and the friction force, produce what we call the turning effect. That is, we shall have the clockwise and the anti-clockwise moment. Now we look at the diagram that we have here that is representing that cyclist who is leaning. If you look at this diagram, we have the reaction, we have the point G where we want to take the moment about, and if you look at this distance from where we have reaction and where we have the action, the point G, that distance is x. And if you recall, when we are calculating the moment, we always calculate the perpendicular distance to the reaction of force and the force. So it is the product of force and the perpendicular distance. So in our case here we have r multiplied by x. If you look at the second one here, we have the friction force that is acting towards this direction, and this is the distance from where we have the point G to where we have the friction force. This distance is the one that is perpendicular. So we proceed as follows. We have r, this one, multiplied by x is equals to fr, this one, multiplied by y. But we know that r is equals to mg. So where we have r, we put mg. So we shall have mg multiplied by x is equal to fr multiplied by y. Then after that, we want to simplify this expression so that one side we have x over y and the other side we have the other terms. So we proceed by dividing through by y. So the y on this side will cancel out, and then we divide by mg. So on one side we have x over y is equals to fr, that is friction force, over mg. And now from there, I want us to look at this angle. This is what we are calling angle theta. If you want to get the tangent of this angle, you need to consider the opposite and adjacent. Remember the SOHCAHTOA. The tan theta is opposite over adjacent. The opposite of this angle is this line, and the adjacent is this height, which is our y. Therefore, it implies x over y is tan theta. So tan theta is x over y. So in other words, we can say that from here we have tan theta is equals to fr over mg. But we know the friction force, which we said that it is the same as the centripetal force, is equals to mv squared over r. And therefore, we replace, instead of writing fr here, we replace with this expression. Therefore, tan theta becomes mv squared divided by r mg. Our m will cancel out and you are left with v squared over rg. That will be our tan theta. From tan theta is equals to friction force over mg, we can be able to get the friction force by multiplying by mg both sides. So we have that the friction force will be mg tan theta. In Form 3, we learned that friction force is always given by mu r, where mu is the coefficient of friction. But here we have seen that the friction force is mg tan theta. Remember, this r is also the same as mg. Therefore, mg tan theta is equals to mu mg. If you look at mg and mg, we have them both sides, which implies that tan theta is equals to mu. And this one means that skidding occurs when tan theta is greater than coefficient of friction mu. Then we move to conical pendulum. In conical pendulum, the bob moves in such a way that the string sweeps out a cone. Look at this diagram. It is moving so that now it is moving along a horizontal circle. The forces that are acting on this pendulum bob is one, the weight, and number two, the tension of our thread or our string. So as you move here, this will be the angle theta, which is equivalent to be with this, and therefore you can be able to get this force as F sine theta, and up there we have F cos theta. Now, centripetal force is provided by the horizontal component of the tension, that is F sine theta. Hence, from the Newton's law, we have that F sine theta, which is now our centripetal force, is equals to mv squared over r. And there is no vertical acceleration. Remember, this bob is just moving on a horizontal circle, which implies that F cos theta is the same as the weight, that is mg. Again, from the two equations, if you are able to divide or to get the tan theta, that is sine theta over cos theta, you will get the same expression, that tan theta is equals to v squared over rg. Note that this equation is similar to the other one we got earlier for the banked tracts. When the angular velocity omega increases, the bob rises, hence theta increases. And this concept is applied in merry-go-round. When you're having the merry-go-round, you find that as you increase the rate of rotation, you will find that the theta goes up and you're able to move up, all in speed governors, as we are going to see later. Thank you, and let us meet in our next lesson.